So in this class, let us see how we can find out the slope and deflection in the case of a cantilever beam. So the first case I will take a cantilever beam with UDL throughout, carrying UDL throughout. So you know that in the case of a cantilever beam, one end is fixed and the other end is free. There is no support at the other end. Here, end A is fixed, end B is free support. It carries a UDL of W per unit length or unit 1. Okay. Span is L. So here, one important thing is you will be having two reactions at the fixed end and there is no reaction at the free end because there is no support at the free end. Same procedure I am going to use which I did in the last video lecture was simply supported beam with UDL. The deflected curve in this case of the elastic curve, since this is fixed to support, there is no deflection, there is no slope at the fixed end. So the deflected shape will be like this. The axis, this is the axis of the beam. The axis of the beam will deflect like this due to the application of this UDL. So this deflection I will take it as YB, and if you draw a tangent here at B to this curve, and that tangent it makes an angle theta B in the anti-clockwise direction with the axis of the beam. So that is the slope. So theta B is the slope or rotation at free end, whereas YB is the deflection at free end. Deflection at free end. So here, this at the fixed end, you don't have any slope and deflection. That means theta A is 0, Ya is also 0. So these are the boundary conditions which we have to use to find the constants of integration C1 and C2. So another thing is here, the distance x is measured from the free end here. So that is the usual procedure in the case of cantilever beam. So x is measured from the free end. Please note, I will consider a section xx at a distance x from the free end. So this distance is x. Whereas in the case of simply supported beam, the distance x is measured from the left support, if you remember. So here I am going to take the distance from the free end. Now the procedure is, first we have to write the that is moment equation, then we have to integrate it to get the slope equation, then we have to integrate to get the deflection equation. Now what I will do here is, I will write the bending moment at xx, which I call it as mx. So see to the right side of this xx, as I already told, downward forces give negative bending moment, that is hogging nature. Upward forces give positive bending moment, sacking nature. Here, only UDL is there. If you see to the right side of this xx section, UDL is acting downward, so minus. Intensity is W, distance is x, so W into x is the total UDL, total load. It acts at the midpoint of this, so into x square. So this is the bending moment equation, minus W x square by 2. So this is equation 1. So this is the moment equation. Now if you integrate moment equation, we are going to get the slope equation. Now as per the Euler's Bernoulli deflection equation, this mx can be equated to Ei into d square y by dx square. This is the Euler's equation. That means what I can write here is Ei into d square y by dx square will be equal to minus W x square by 2. So now this becomes equation 1. integrate with respect to x both sides, you are going to get what is called as slope equation, that is di into dy by dx. Integration of d square of dx to dy by dx is equal to minus w by 2 is constant into integration of x square is x cube by 3 plus constant of integration c1. So this is also written as theta. Dy by dx is nothing but theta. This is slope of rotation. So that means you will get E into theta is equal to minus w by 6 x cube plus c1. This I will call as equation 2. Now once again, if you integrate this slope equation, that is equation 2, you are going to get what is called as the deflection equation. So dy by dx integration is y. So therefore ei into y is equal to minus w by 6 into integration of x cube is x power 4 by 4 plus c1 x plus c2. Or in other words, it is minus w by 24 x power 4 plus c1x plus c2. So this is equation 3. So the first equation is the moment equation. If you integrate moment equation, you get slope equation. Second equation. Next, if you integrate slope equation with respect to x, you are going to get the deflection equation, that is equation 3. Now, to get these two constants of integration c1 and c2, you have to use the boundary conditions. So two constants are there, two boundary conditions were required. I have written here the boundary conditions. At x is at b, first boundary condition is at b, theta is 0. There is no at a theta is 0. That is theta a is 0. No? So at a theta a is 0. And what is the value of x at a? X is equal to L. Please note that x is measured from the free end. So therefore, from free end to a, this distance is L. So at x is equal to L, slope is 0 at the fixed end. So substitute this in the second equation. Substituting for theta and x in second equation, ei into theta becomes 0 now. So ei into 0 is 0. 0 is equal to minus w by 6 x is L cube plus c1, or in other words, c1 is equal to w by 6 L cube. So this is one constant of integration. Now the second constant of integration you can get using the second boundary condition. Second boundary condition is at the same point A, at the fixed end, slope is also 0. There is no slope here. So at A, once again x is equal to L, y is also 0. This is the second boundary condition. So substituting in equation 3. Second equation is slope equation. Third equation is deflection equation. So you have to substitute this in deflection equation. So once again here, En into y is there. So this y becomes 0. So Lx becomes 0 is equal to minus w by 24 L power 4 plus c1. I can substitute for c1 as plus w by 6 L cube plus c2. Now from this you can simplify for c2. So c2 is equal to this minus this, that is wl power 4 by 24 minus wl cube by 6. So this is the value of one second. So c1 here into one more l into there here, because x for x also I have to substitute. X is l here plus l. Yes. That means this is wl power 4 by 24 minus wl power 4 by 6. So LCM becomes 24 only. So this becomes wl power 4 minus 4wl power 4. So finally it becomes C2 is equal to minus 3 times wl power 4 by 24 or minus wl power 4 by 8. So now we got the constants of integration C1 and C2 by using the boundary conditions. Now I will substitute for C1 and C2 in the equations 2 and 3 to get the final slope and deflection equations. So substituting substituting in equation 2, EI into theta is equal to minus W by 6 x cube plus C1 is plus W by 6 L cube. So this I will call as equation 4. So equation 4 is nothing but equation 2 only after substituting for C1 and C2. Then the next equation 3 becomes EI into Y. EI into Y is equal to minus W by 24 into x power 4 plus C1x means plus W by 6 L cube x plus C2 is minus W L power 4 by 8. So this is the equation 3 after substituting for C1 and C2. So I can simplify this. Okay, W x power 4 by 24. Okay, let it be like this only. So this is equation 5. So equation 5 is nothing but equation 3 after substituting for C1 and C2. Now using these two equations, so this is the slope equation, final slope equation. This is the final deflection equation. In these equations, if you substitute for x, so you can get the values of slope and deflection at the required point. So let us find out the value of x. Let us find out the value of slope and deflection at b, at the free end b. At the free end b, you know that x is equal to 0 because x is measured from the free end only. So at free end, I need the values of the free end. At free end, that is at b, x is equal to 0. So we have to put x is equal to 0 at the free end in these two equations. So if you substitute in equation 4 as x is equal to 0, you will get EI into theta b, because theta becomes theta b, that is the slope at b is equal to, put x is equal to 0 here in this. So first term becomes 0, second term is plus W by 6 L cube, or in other words, theta b is equal to W L cube by 6 EI. W L cube by 6 EI. So you can see that this is anti-clockwise. Therefore it is positive. So anti-clockwise is positive, clockwise becomes negative. So this is the slope at the free end. Slope at free end. Similarly, if you want deflection at free end, which is maximum, you have to put x is equal to 0 in equation 5. So it becomes EI into YB. YB is the maximum deflection. Please note that at the free end, you have YB, that is Y max, in case of a cantilever beam. So substitute in this equation x is equal to 0. So 0 plus 0 minus W L over 4 by 8. Minus W L power 4 by 8. So that means here YB, if you want, so YB will be minus W L power 4 by 8 EI. If you bring the EI to RHS, it becomes divided by EI. So this negative sign indicates that the deflection is downwards. So this is deflection at free end. That means when a cantilever beam is subjected to UDL throughout, slope at the free end is given is WL cube by 6 EI, deflection at the free end is minus WL power 4 by 8 EI. So here we are using the boundary conditions, both the conditions at the fixed end, because at the fixed end both slope and deflection is 0. And another thing is always distance is measured from the free end. So at the fixed end means here x becomes L. X is equal to L here, x is equal to 0 here, then x is measured from in this direction. This is one case when the cantilever beam is subjected to UDL throughout. So these are the expressions. Better you remember these two expressions, slope and deflection expressions. Next, this of course is used in checking the maximum deflection in the case of a cantilever beam when you are designing using IS 456 code. Now the second case, what I do here is cantilever beam only, but I will take concentrated load at the free end. So cantilever beam with point load or concentrated load with point load at free end. So in this case, what happens? Here also maximum deflection occurs at the free end only. The figure will be like this. I will take A as the fixed end, B as the free end, E and I, hence modulus and moment of inertia, texture rigidity of the beam. So this will take as capital W is the point toward the free end, L is the span. So in this case also, the deflected curve due to this load, it will be like this. So this is YB, and as usual, if you draw a tangent here, so whatever angle made by the tangent with the axis of the beam or x-axis, so that is the slope. Now here also x is measured from the free end. So x is equal to 0 here at B, whereas x is equal to L at the fixed end. Same boundary conditions. So I will consider a section XX here. Once again, a distance x from the free end here. So this YB becomes Y max in this case also. So let me write the bending moment expression at XX here. So I am writing in the same manner, bending moment at XX. See to the right side of the section, only one force is there, downward force, bending moment to downward force is negative, minus W into X will be bending moment. So as according to this Euler's equation, deflection equation, Mx is Ei into d square by dx square. We can equate these two now, therefore I can write like this, Ei into d square by dx square is equal to Mx means minus W x. So this is the moment equation. Moment equation. If you integrate this moment equation, that is equation 1, you will get the slope equation. Now let us integrate that with respect to x. We have to introduce one constant of integration C1. Then once again, if you integrate that slope equation, you are going to get the deflection equation, that is y equation, and another constant C2. So those C1 and C2 constants, they are evaluated using the boundary conditions applied at the fixed end B. Now I will continue here. Integrate with respect to x. So it becomes dA into dy by dx is equal to minus W is constant, integration of x is x square by 2 plus constant of integration C1. So this I can call as equation 2. Next, once again, so this is the slope equation. Slope equation. Now once again, if you integrate with respect to x. So that is the double integration method. dA into y, you are going to get y now, is equal to minus W by 2 into x cube by 3 plus C1x plus C2. So that means it is minus W by 6 x cube plus C1x plus C2 equation 3. So 1 is moment equation, 2 is slope equation, 3 is deflection equation. Now to evaluate these constants of integration C1 and C2, we have to use the boundary conditions. The boundary conditions I am going to apply at the fixed end as usual. At the fixed end, x is equal to L. First boundary condition is at A, x is equal to L, theta is equal to 0. Please note that at the fixed end, theta is 0, y is also 0. These are the boundary conditions. So you have to substitute this in the slope equation. That is equation 2, because theta is involved. Substituting into, so we know that theta is 0 means, so this is nothing but theta. Please note that dy by dx is nothing but theta. So here, if you put 0 for this, LHS becomes 0. 0 is equal to minus W into x is L, so WL square by 2 plus C1. So therefore C1 becomes WL square by 2. So this is one constant of integration Second constant of integration is obtained by using the second boundary condition. Second boundary condition is at A, it is at the fixed end. Once again, x is equal to L. Deflection is also 0, y is also 0. Since deflection is involved, we have to substitute in the third equation. Substituting in 3. Substituting in 3. So LHS becomes once again 0, y is 0, is equal to x is L here, minus W L cube by 6 plus C1 is W L square by 2 into x is once again L plus C2. So from this we can get the value of C2 now. So C2 is equal to W L cube by 6 becomes positive, this becomes negative, minus W L cube by 2. So 6 is the LCM, W L cube into 1 by 6 minus 1 by 2, W L cube into 6 is the LCM. So you will be having 1 minus 3. So finally C2 can be written as minus 2 W L cube by 6 or minus W L cube by 3. So this is the value of C2. Now substituting these two values of C1 and C2 in 2 and 3, you will get the final slope and deflection equations. Substituting for C1 and C2 in 2 and 3. In 2 and 3. Suppose if I substitute in equation 2, so here in this equation, EI into theta will be equal to minus W x square by 2 plus C1. So plus C1 is plus W x square by 2. So this is the final slope equation and called as 4. Then equation 3, substituting in equation 3, that is the deflection equation. So this equation EI into y is equal to minus W by 6x cube plus C1x, that is plus W L square by 2x plus C2, that is minus W L cube by 2. So this is the final deflection equation, equation 5. Now we need the value of slope and deflection at the free end. So at the free end, x is equal to 0, you know that. So if you put x is equal to 0 in 4, so you will get slope at theta b is obtained. Slope at b is obtained. So LHS becomes EI into theta b is equal to, put x is equal to 0 here, this term becomes 0 plus W square by 2 you will get, or in other words theta b is equal to W square by 2 bi. You can see that the value is positive, that means the slope is anticlockwise. Next, if you put x is equal to 0 in equation 5, put x is equal to 0 in equation 5, you can get yb or y max. Maximum deflection occurs at the free end only, is obtained. Now the LHS becomes equation 5 EI into yb or y max is equal to, here x is equal to 0, first term is 0, second term also becomes 0 because it involves x here, minus W L cube by 3, or in other words yb or y max will be equal to minus W L cube by 3EI. So this minus stands for downward deflection. So that is the maximum value of deflection at the free end. So please note the difference between the UDL case and the concentrated load case. Procedure is same. So you should correctly write this moment expression. This is very, very important. If this is wrong, all the further steps will be wrong. So moment expression, write it correctly, then integrate it, introduce one constant, then once again integrate it, introduce another constant. Those constants of integration C1 C2 are obtained from the boundary conditions. In the case of cantilever, you are doing both the boundary conditions, we are applying at the fixed end. So fixed end is here. Always know that x is measured from the free end, so that fixed end becomes x is equal to L. X is equal to L of the fixed end. Theta is 0, y is 0 to fixed end. Using those two conditions, we can find out the constant of integration. Substitute back in the slope and deflection equations. Then wherever you want the slope and deflection, you can easily find out the values. Here I have found out the value at the free end only. Suppose if you want the slope and deflection at midspan point, let me write that. Midspan point means here. For the same problem, if I want the slope and deflection at the midspan point, let us take like this. So B, A, midspan point is here, C, that means X, this is L by 2. This is also L by 2. For this case, if at all I want to find the slope and deflection at this point C, so your deflected shape won't change, it will be like this only. But here I need the value of YC. So this value, deflection at C means this value is YC, and slope means you have to draw a tangent here to the curve, and whatever angle is made by this tangent with the horizontal or with the axis, that is theta C, slope at C. It is not maximum. So if you want the slope and deflection at midspan point, put x is equal to L by 2 in the equations 4 and 5. That's all. So I will write here midspan point, midspan section of point. You can write whatever it is, section, that is at C. X is equal to L by 2 because x is measured from the free end, so this distance becomes L by 2. X is measured from here, so I have already told x is L by 2 here. Put x is equal to L by 2. From equation 4, if you put in equation 4, you get the slope. So EI into theta C, right, is equal to minus W by 2 into L by 2 whole square. X is L by 2 here plus W L square by 2. So this is the equation. Simplify this. Minus W L square, I can take it outside. It becomes minus 1 by 8. 2 square is 4, 4 into 2 is 8. Plus this becomes 1 by 2. I will take comma. So minus, so this becomes minus, this becomes plus. W L square I have taken outside. So here 8 is the LCM. So minus 1 plus 4. So it becomes 3W L square by 8. So this is the expression. Therefore, theta C is, this is the slope at C. That is rotation or slope at C is 3W L square by 8 EI. You bring that EI to RHS. Here also you can see that slope is positive, that means it is anticlockwise. Okay, theta C is anticlockwise. Next, if you use equation 5, you will get the deflection. So the equation 5 is this. So I will write EI into y becomes YC is equal to minus W by 6 into x is L by 2 whole cube plus W L square by 2 into L by 2, x is L by 2 minus W L cube by 3. So let us simplify this. Minus W L cube by 2 cube is 8 into 6, 48 plus W L cube by 4, 2 into 2 is 4 minus W L cube by 3. So if I take W L cube common, minus 1 by 48 plus 1 by 4 minus 1 by 3. So I think 48 is the LCM, W L cube into 48 is the LCM, minus 1 plus 12 minus 16. So finally it becomes 12 minus 7 is minus 5. So minus 5W L cube by 48. In other words, if you want YC, minus 5W L cube by 48 EI. EI if you bring to the RHS, it comes to the denominator. So this is the deflection at C. Negative sign indicates that it is downward deflection. So this is how we can find at any point. Suppose if you want to find the slope and deflection at the quarter point means x is equal to L by 4, you have to substitute. So 3 by 4 point means 3 by 4 L. So like that, if you want to find the slope and deflection at any point, just put the value of x in the final slope and deflection equations and get the values. So in the numerical problems, even the EI value will be known. So all these will be known, W, L, E, I, everything will be known. You can get the value of the deflection in radians and slope in millimeters. So that next class I am going to explain the numerical examples.